So, very good evening to everyone. My name is Aryan, and in this particular presentation, I'm going to talk uh, a little bit about basically the photon picture of light, and then later on, I'm going to talk about one of the most fundamental experiments of quantum physics, that is the photoelectric effect. Now, to give you just a little bit of idea about the photon picture of light, we all know that this has been one of the most discussed topics in the physics community in the probably in the 19th century, that whether to consider light as a collection of what Sir Albert Einstein and Sir Max Planck called quanta, discrete quanta. That is, you can basically count the number of particles that are that, that 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 the light is made of. Basically, one quanta, two quanta, three quanta. Every quanta has its own set of energy and momentum, just like any other ordinary material particle. Or to consider light as a collection of not as a collection, but as basically an electromagnetic radiation. Now, an interesting picture that I have depicted here is that we have one source of light, let's say this candle. On the left hand side, this same source of light triggers what we call as the Compton effect, whereas wherein we consider this light as basically collection of photons, and this photon when collides with the electron, you have basically the Compton effect. On the right hand side of this same source, we have what we call as the double slit experiment, which can only be explained using the wave theory of light. So basically, same source of light on the left hand side, it may trigger a Compton effect. On the right hand side, this same source of light may show that I am a wave. Now, photoelectric effect that we are going to talk in this presentation basically gives a strong conclusive evidence that this source of light which we are talking about is nothing but collection of discrete quanta. That is, you can count the number of quantas, one quanta, two quanta. Every quanta has its unique linear momentum and has its own energy. Now, few properties of this quanta, which Albert Einstein called photons, is as follows. First property is that they travel with the speed of light, which is 3 into 10 raised to the power 8, very basic. Second property about these photons is that these photons are massless. That is obviously in the rest way. That when you try to weigh these photons, or when you try to observe the weight of these photons, the mass of these photons in the rest frame, it comes out to be zero. And it's a consequence of special theory of relativity. We can just spend a minute on the proof of this. So we know this famous equation E is equal to mc square, which is the energy mass equivalence. This m here is the relativistic mass. We can write this as m naught over under root 1 minus v square by c square times c square. This m naught is the mass in the rest frame. This is what we are looking for. If we solve for m naught from here, this m naught comes out to be e over c square under root 1 minus v square by c square. From the first point, we know that the velocity of light, we can substitute velocity as c, and this c square and c square cancel off, and this m naught becomes 0. So we have the rest mass of a photon as 0. Third point, which I would like to emphasize, is that energy of a single photon is E is equal to h mu. So basically, we are as I already discussed, that um, every photon has its energy as well as its linear momentum. तो यहाँ पर हम देख सकते हैं कि जो एनर्जी है एक सिंगल फोटोन की वो एच सी बाय लैम्डा होगी, और जो लीनियर मोमेंटम है सिंगल फोटोन का वो पी इज इक्वल टू एच बाय लैम्डा होगा. ये हमने define करा है both energy as well as linear momentum. This h by lambda value can be substituted from above as E by C, and we have the relation between the linear momentum and the energy, that P is equal to E by C. Now, I can say that this, if you look at this second equation, if we talk about the linear momentum, in general sense, a wave does not have a linear momentum, right? It's only the particle which has the linear momentum. And on the right hand side of this equation, we have lambda. In the classical sense, a particle does not have wavelength. It's the wave that has the wavelength. So basically, we can say that these particular set of equations, equation 1 and 2, act as a bridge between particle and wave nature of light. A very, very interesting fact. Now, in this particular set of in this particular presentation, we are often going to use the intensity of light. Now, in the fourth point, I have tried to clarify that intensity of light has got nothing to do with the energy, basically the energy of the electromagnetic radiation or energy of what we now call as photon. Intensity of light only means more number of photons. So we say that we increase the number of we increase the intensity of light. That would directly mean that we are increasing the number of photons. It has got nothing to do with the energy of light, okay, or the energy of electromagnetic radiation. Now, after having our basics cleared, we are proceeding towards the photoelectric effect. The definition of photoelectric effect is that when light of sufficiently low wavelength falls on a metal surface, electrons are ejected out, and these electrons are called as photoelectrons, and this effect is called as photoelectric effect. It's a very, very simple effect. You have a metal, and it says that when light of sufficiently low wavelength, it means that we are using a source of light which has very, very low wavelength, okay, and when that source of light is incident on a metal surface, the electrons come out of the metal surface, okay, and these electrons are called as photoelectrons, and this effect is called as photoelectric effect. Now, you all know that there are large number of free electrons inside a metal. How many? When we say that there are large, how much? So basically, to give you a fair idea, you all of you must have heard about the Avogadro's number. So for example, if we say that 63.5 gram of copper has approximately 10 raised to the power 23 atoms. Yeah. So basically, we can say even if one atom contributes one free electron, we can easily say that 63.5 gram of copper has approximately 10 raised to the power 23 electrons. So you must understand that we are talking about huge number of electrons. Okay, even 1 gram of copper, it is easily it can be easily seen from this that 1 gram of copper will almost have 10 raised to the power 21 or 10 raised to the power 22 atoms, and if one atom contributes to one free electron, you are talking about huge number of free electrons. Okay, so every metal has large number of free electrons. That's why they are good conductors. Okay, so though these electrons are free, okay, the electrons that we are talking about, though we are calling them as free electrons, but remember the electrons, the photoelectrons have to be ejected out of the metal surface. It's not an easy task. See, every electron that we are talking about, whether it's a free electron, whether it's a bound electron, it is attracted towards metal by some work function, okay, by some work function. For example, for if we talk about cesium atom, for example, cesium atom, it has got work function of about 1.9 electron volts. So basically, you have to supply this 1.9 electron volt of energy in order to get one electron ejected out of the metal surface. Okay, so what happens in photoelectric effect, right? So we have the electromagnetic radiation, which we call as light, which we now say that this electromagnetic radiation, it's not a wave anymore, but it's just the collection of quanta or collection of photons. So what happens in a very ideal situation? In a very ideal situation, we can say that a photon collides with the electron and supplies all of its energy to the photon. So this is the electron, it collides, not an electron. So this is a photon basically, and though photon is a particle, still just for the simplification, I am representing it by a wave. This collides with the electron and supplies all its energy to the electron. This is a very ideal case. It supplies all its energy to the electron. It's a photon. Remember, it's a particle now. Light consists of large number of photons. We'll say that light contains large number of photons. So when this photon, which is we are shining this collection of photons onto the metal, which it's a free electron, right? It's a free electron. We are shining this electromagnetic radiation onto this metal surface, and this photon, when it collides with the electron, and in the very ideal case, this photon supplies all its energy to the electron if that energy is greater than the work function. If greater than the work function, this electron will come out from the metal. Okay, electron comes out from the metal. Now we must understand that though though E greater than work function is some criteria for the electron to come out from the metal, it is not necessary that if the energy is greater than work function, then for surely we can say that the electron will come out from the metal. This is not necessary. Maybe we have supplied energy to the electron, and that electron probably it collides with the other electron and it consumes all of its energy in the collision, so that it does not have the sufficient energy to come out from the metal surface. This can also be the situation. So therefore we are targeting the electrons which are close to the surface, because the electrons that are close to the surface will have lesser probability of collisions, and maybe the photon transfers all of its energy to the electron, and the electron comes out from the metal surface, overcoming the overcoming the work function of the metal, and in a very fortunate case, it can have some of its kinetic energy as well. So we can say that the kinetic energy maximum, we are talking about the maximum kinetic energy of this photoelectron. It will be equal to the energy, basically the energy that we are supplying minus the work function. This will be the maximum kinetic energy of this photoelectron, because remember, E is the energy that the photon has. E is the energy of the photon, and we are assuming that the electron with which this photon collides does not undergo any collision with the rest of the electron. It just has it just has to overcome the work function of the metal, and therefore the this E minus phi, the rest of the energy that remains is the kinetic energy. And remember, this is the maximum kinetic energy. So basically, the kinetic energy of that photon may vary from 0 to this particular set of kinetic energy, E minus phi. Why 0? Because there is a possibility that this E minus phi becomes 0. That is, we have supplied the energy to the to the electron, and it consumes all of its energy in the collision, and it just has some energy to get out of the metal surface. So in that case, the kinetic energy of the electron may be zero, right? We have just supplied the energy which is just equal to the work function of the metal, and therefore the kinetic energy is zero, right? So we can have such situation as well. Now, from equation maybe one, we just have to see. Yeah, from equation one, we can write this kinetic energy, this energy E, we can write this as hc over lambda minus psi. And this is a very, very important equation. Let me write it down again. Your kinetic energy maximum is hc over lambda minus psi, which is the work function. It's a very, very important result. Now, remember at the beginning when I talked about the definition of photoelectric effect, and I said that we must have some minimum wavelength. Let me, let me show. Yeah, when the light of sufficiently low wavelength. Now, what happens if we supply if the wavelength of the light that we are using is greater than this particular wavelength, or basically what is the concept of this low wavelength? Now we must understand from this particular equation that there is some certain value of lambda for which this photoelectric effect will work, right? So there is some threshold wavelength. There is some threshold wavelength, and there is some threshold wavelength, and if we just look at this expression star, if we just look at this expression star, if you put lambda to be equal to, let's say, hc over psi, okay, if we put this lambda equal to hc over psi, hc and hc cancels off, psi minus psi becomes zero, and in that case the kinetic energy becomes zero. Remember, this is the maximum value of this lambda naught, right? Because if you put any other value of this lambda, this kinetic energy is either positive or it's negative. Kinetic energy in the classical sense cannot be negative. Therefore we are defining threshold wavelength lambda naught as hc over psi. I hope you get the logic. If you put this lambda naught in place of this lambda, it will be hc over psi. Hc cancels off, psi minus psi becomes zero. Therefore this kinetic energy becomes zero. This lambda cannot be basically the wavelength of the incident light that we are using cannot be greater than this lambda naught. This has to be the maximum threshold wavelength. If this lambda becomes greater than becomes greater than this lambda naught, the kinetic energy becomes negative, which is not possible, and therefore the photoelectric effect will not happen. We can look this from another point of view as well. If your lambda becomes greater than lambda naught, we just saw that E is equal to hc over lambda. Yeah, E is equal to hc over lambda. So basically if lambda becomes greater than lambda naught, the energy will be much smaller, because this lambda and this energy are inversely proportional. If lambda becomes greater than lambda naught, then E will be smaller than the work function. Then energy would be smaller than work function. Smaller than work function, and then no electron comes out. So this is the basic funda of this minimum of this maximum wavelength. Sorry, this has to be the maximum wavelength. Any wavelength lesser than this lambda naught is allowed, but if lambda becomes greater than lambda naught, there are two explanations to that. If lambda becomes greater than lambda naught, this kinetic energy becomes negative. And also, if lambda is greater than lambda naught, from this relation, you know that energy becomes much smaller. And if energy becomes much, much smaller than the work function, then we know that no electron comes out. Now, we also know that there is a relation between frequency and the wavelength, that mu is equal to c over lambda. Basically, if we put lambda naught instead of lambda, we have your mu naught is c over lambda naught. Okay, and this is nothing but this psi over h. Yeah, this psi over h. Because obviously, if you put c by c over lambda naught from here, this becomes psi over h. So basically, this is the threshold. Like here we were talking about the threshold wavelength. This can you can also talk in terms of the frequency, that this will be the frequency, this will be the minimum frequency that is required in order for you in order to conclusively say that photoelectric effect will happen. Otherwise, the photoelectric effect will not happen. So this was in general the idea. We can just substitute probably if we look at this. If we look at this equation. Yeah. Okay. If we look at this equation number star, we can substitute uh, the value of kinetic energy maximum will basically be h mu minus, we can substitute the value of this work function as mu naught h. We can take this h as common. You have mu minus mu naught. So we have another interesting relation, that kinetic energy maximum is equal to h times mu minus mu naught. Probably in the next set of lecture, we are going to talk about the experimental setup of this photoelectric effect, that how basically we are going to perform this set of experiment in our laboratory. Till then, thank you very much.